friend and colleague from the University of Utah, Christoph Boehme. Christoph got his PhD officially from the University of Marburg in Germany, but the work that he did was done at the Hans Meitner Institute in Berlin. He came right from there in 2006 as an assistant professor at the University of Utah. Has been there ever since, has been tenured, is now a full professor. And his work, I would say, if I had to briefly characterize it, would just say he does work on spin physics in small ensembles is one way. Another way, and where he got really well known, I would say, is his work on spin-dependent recombination in various semiconductor materials, and he's expanded that, and I'll tell you a little bit about that, into things like organic semiconductors. And that's where I got really to collaborate with him, is when we were working together on spin physics and organic semiconductors in the few years shortly before I left to come here. So it's my pleasure to introduce Christoph. He's going to tell us a little bit about what his group works on, and then again, I hope you'll enjoy socializing afterwards. Thanks, Christoph.
All right. Thank you very much. Thanks, Brian, for the kind introduction, and thanks everyone for being here, for showing your interest, and for having me. I've had a wonderful time. I'm humbled by this wonderful reception, to meet all the people, to see all the exciting research, to be here for the first time. I've not just wanted to come to Pullman since Brian moved here. We tried to hold him back, but then I see all the reasons why he left. But I've wanted to come for a long time also, because I've known Matt for a few years. So great place, exciting. And yes, what am I doing in a broader sense? Yes, my research it includes a lot of physical systems and a lot of topics when you look at the surface. But the underlying interest has indeed been, as Brian pointed out, into the nature of spin selection rules and spin-dependent processes in a broader sense in condensed matter systems. And yes, today I talk about this, we have to talk about what that actually means, the spintronics of weakly spin orbital coupled materials. What are weakly spin orbital coupled materials? Weakly spin orbit coupled can only be electronic states, but you find those predominantly when you look at condensed matter systems that are made out of light elements, when you go very far up into the periodic system. And then you see, of course, yes, technically that includes silicon-based materials, but also this whole universe of carbon-based materials. And that by itself then includes organic semiconductors. So now we are talking about the spintronics of organic semiconductors. Now, what are organic semiconductors? What can we do with them? Organic semiconductors, a lot of people are not aware of this, really has found its way into technologies. I mean, devices based on organic electronics have been, I recently read, I would have a hard time though pointing out to the source, but I could look it up somewhere in one of these IDX reports or whatever, that it's now a $26 billion business and growing apparently. And that is, why is it? Because of essentially that. So these materials are able to provide electronic transitions that produce beautiful colors, but then they're also very easy to process. They're fairly cheap. They are mechanically flexible. That's why we have these bend screens nowadays, versatile, and you can do a lot of interesting things technologically. That's why they are big. However, when we now say, well, here we have now established materials for some electronics, why don't we do spintronics? Of course, you can ask then, why do we even want to do that? And the important part in this context is exactly are not the properties for what we know them for, so forget about all that, but instead, it is weak spin orbit coupling. It's carbon-based, so predominantly electronic states. You cannot generalize this because it's not a question of material, it's a question of the nature of electronic states. They have weak spin orbit coupling. And that is what causes a number of interesting effects that are related to spins and to the electronic behavior, the general physical behavior of these material systems. And that, if you look at all the people who look into study these materials in the context of spin manifolds, my way to look at this is by categorizing this into two work domains. And the first one is related to spin polarization effects. That's usually what physicists refer to as spintronics. Essentially utilizing effects that are all about the injection of polarization, the detection of polarization, and then the propagation of polarization, meaning spin transport, and then spin orbit mediated spin manipulation schemes that people have been thinking about in the terms of spin transistors. And yes, people do study these topics and these mechanisms in organic semiconductors and other carbon-based semiconductors because weak spin orbit coupling can imply in certain systems that you have very long spin relaxation times, spin lifetimes, and that translates then into very long spin diffusion lengths. And so from that point of view, you would say, well, that's the best group of materials to build spintronics out of. And that's all true. But oftentimes you realize that these materials also have low charge carrier mobilities. And since spin diffusion length is actually governed by mobility and spin relaxation times, so you see already what you gain on one side and you lose on the other side. But then, then of course you can start talking about building materials with weak spin orbit coupling based on carbon that have high mobilities. And maybe then you can, essentially get these advantages from two sides. But this is basically one research area that I would call traditional spintronics. And then there's the other half that some people, and that's not my invention, but I think that goes back to, it may have been David Avshalom who referred to this other area as quantum spintronics, simply because it's spintronics of systems where you have long spin relaxation times, and therefore quantum mechanical propagation becomes much more relevant for these properties. And that is actually, I would categorize this as the area where you see effects of spin manifolds on materials properties and behaviors that are not even related to polarization. And this is what I'm going to talk about today. And that is, you would say, what is the effect then, if it's not related to polarization but spin? That's predominantly due to spin selection rules and what they can do in these materials. Now, what are spin selection rules and what they do? And I want to start here with basically the most simple examples that I can think about, and that is Pauli blockade. And I think now this thing is stuck. Let's see. Yeah, now nothing goes. Let's try again. Okay. And no. Okay. Then. That's interesting. All right. Computers always find the right moment to be difficult. Hang on. Wow. Okay. So here's my example with some delay. Of course, I wanted to build up suspense. It was all intended. But something very simple. You take a pair of copper coils, build a Helmholtz magnet so that you have it doesn't even have to be a homogeneous magnetic field. You create a magnetic field, but what this is supposed to illustrate, a low one, where you have a few millitesla, if at all, magnetic field. And now you take a layer of an organic semiconductor, a polymer. In this example that I'm talking for now about its MEH PPV, that goes back to the 1970s. That was kind of the prototypical organic polymer, conducting polymer material where you can inject charge carriers. And if you want to do this, you need additional layers. Do we have a laser pointer, actually? No, doesn't matter. So where you have several layers, let's say calcium, and then what's another polymer called P dot, and now you can inject electrons and holes. Essentially, you can build an asymmetric device where you can create a non-equilibrium. You can also call the whole thing diode. In fact, you can call it organic light-emitting diode, because if you have then recombination, it even produces light. But that's not the point here. The whole point is you can apply a bias, you have charge carriers, and because you apply a bias, you will have a current. And then if you let it sit, then you have a constant current. And if you, let's say, you apply whatever you want, but if you have a device where you apply 50 microamps, and now you change your magnetic field. In other words, you carry out a magnetoresistance measurement. The changes of your conductivity, the changes of your current on an incredibly small time scale is really huge. So this is not giant magnetoresistance where you have changes in the tens of percentages, because if you look at the percentage, at the fraction of change, well, it is large, but it's in the percent range, not in the tens of percent range. But the change per magnetic field is just outrageous. And how is this supposed to work? Why do these materials do that? Because naively you would say, well, first of all, can it be just some sort of Lorentz force effect on charge carriers? And you can rule that out very quickly. That doesn't work like the Hall effect. So it's really a spin effect. Fine. But if spin controls somehow electric current and charge transport and or recombination, because we have a non-equilibrium here, then if spin controls current, you look at the polarization. This, by the way, it's a room temperature, this room temperature data. So obviously at 0 millitesla, you have no magnetic polarization. Now you turn on your magnetic field to, I don't know, 5, 6 millitesla. Guess what? You still don't have magnetic polarization. You don't change anything about the polarization. For all practical purposes, polarization is 0. Yes, it's not 0, but 10 to the minus something. How can you have percentage range changes? And so, again, that's my standard example for a spin selection rule. People have studied decades to study this, and what actually happens is because of the injection of charge carriers, your whole device is in a non-equilibrium. That means, however, it is of course in a steady state, and under these steady state conditions, what you do is, well, you have a constant recombination rate, which has a significant fraction of your overall current. And the recombination pathway illustrated here by this sketch, again, people put decades into this to figure this out. This is a two-particle picture that represents this. What happens is charge carriers find pairs, which eventually will recombine. But before they do this, they form intermediate pairs. And these intermediate pairs happen to be pairs of paramagnetic states, 2 spin 1/2, electrons and holes, with weak spin coupling, so low exchange and dipolar coupling, and also very weak spin-orbit coupling, so electronic transitions require spin conservation. And what that means is you build in the steady state densities of different spin manifolds. Triplet states, singlet states, but because of spin conservation, Pauli exclusion principle, the decay of these pair states is much, much faster for singlet states than triplet states. And that means in the steady state, you simply pump triplet states. You create, of course, as many states with triplet content as states with singlet content, and you pump them to higher and higher densities, but the singlets get flushed out and you're stuck with triplets. So you pump triplets just by turning on this device. And what now happens when you change the magnetic field is, all you do is you essentially change, you have your externally applied magnetic field that slightly shifts these levels, and these levels now compete with local hyperfine fields. These are local magnetic fields in these materials. Where do they come from? They come from the all-abundant hydrogen, because hydrogen nuclei have a magnetic moment, and every electronic state, these localized electronic states, only interact with a few hydrogen, and the net field of those is, expectation value is 0, but for any given state, it's somewhere between minus a millitesla and plus a millitesla, and you just have to outdo these fields in order to change the permutation symmetry within your charge carrier ensemble. And that's the whole trick. And so you see how these non-equilibrium processes allow you, by changing, in this case, in this example, permutation symmetries, and you know, if you look at the energy scales of these shifts, we are talking about nano-electron volt to maybe lower micro-electron volt range, so orders of magnitude below the thermal energies, but that completely allows you to switch permutation symmetry ratios and therefore your recombination rates. How can we test this? That's the interesting data. You repeat this experiment, magnetoresistance measurement, in the same way after essentially introducing a copper coil to your experimental setup, and then you apply an RF radiation. And what this can do is, at the appropriate magnetic field, if you choose the right frequency, introduce magnetic resonance. And you would say again, you know, under these magnetic fields, doing magnetic resonance requires RF radiation, and we're talking about energy Zeeman splittings in the nano-electron volt range. Excellent, thanks. In the nano-electron volt range, you can do magnetic resonance there. You would, with inductively detected magnetic resonance, you would never get a signal. But then if you look at these rates, then you do get a signal. So same experiment. So now we have the red data, that's our magnetoresistance measurements. Green data looks almost the same, but only almost. There's a slight deviation here at around 3 millitesla. And if I look at the difference between these two measurements, then I get a dependence of that difference that looks like this. And again, this is now an electrically detected magnetic resonance measurement where you see the imprint of, you know, if you analyze this, you end up with two lines that have the same G value, roughly 2, as expected for weak spin orbital coupled systems, that correspond to electron and hole resonances. And so that's a way to measure EPR. And again, in absence of polarization, there's no thermal polarization. Again, what you do is you carry out magnetic resonance transitions between permutation symmetry states. Now, why is this so weak? You know, if external magnetic fields change rates and magnetic resonance does the same, why is that change so weak? Because these lines are so wide, and these lines are so wide because they are governed by the local random distribution of hyperfine fields, the proton-induced local magnetic fields. And because of that, if I apply, let's say, 4 millitesla here, and then I have magnetic resonance with pairs that correspond to this signal, then I only apply a small subensemble that correspond to these 4 milliteslas. And that's a small fraction of the overall ensemble of charge carriers. How can I test this? I repeat the whole experiment, except with the same molecule and the same compound and the same device structure, so the so-called MEH-PPV. And however, I substitute all the hydrogen by deuterium. So I have smaller local magnetic fields, and all of a sudden my signal gets stronger and the line gets more narrow. And so that's kind of the ultimate, you know, the ultimate proof that essentially the stories that I explained here really works. And now, of course, now you see we have about 1/6 of the change that magnetoresistance produces here. So this works really well. This shows the sensitivity of the properties of these devices. And actually, it also shows that these devices that I've been talking about, like these devices that you see when you look at that, are governed by these spin selection rules. And in fact, optimizing these display devices means nowadays mostly addressing the glass ceilings of efficiencies which are governed by spin selection rules. I would actually argue that an OLED display is a Spintronics device if you use the definition of Spintronics as a device that whose behavior depends on spin manifolds. But then the question is, how do we define Spintronics? But okay, so following this, now you would say, great, so we now understand what's happening and we can actually use this for magnetometry. So this is one device concept that came out of this work, really as an invention for technology. So since we can detect Zeeman split states magnetic resonantly without any polarization, we can do it at almost arbitrarily low magnetic fields and frequencies. Using magnetic resonance-based magnetometry is as old as magnetic resonance. People have been doing NMR magnetometry since the, I would guess, 1940s. No, actually, early 1950s. That's when this really started. But it's always been used at high magnetic fields. It's used as for calibrations of NMR experiments. Now you basically can extend this linearity to really low frequencies and therefore magnetic fields and use it as a sensor. And you can also, because it's based on electric current, electric measurements, electric currents in thin film devices, you can implement this as a monolithic thin film device where you essentially have these bipolar injection devices that you combine with an RF source that is produced also by a thin film layer. So we've been pursuing this for a few years. Started out with a patent. What you do is you sweep your frequency and see where you get your current change signal. This is a derivative signal detected due to the amplitude modulation of your excitation. And then if you see the zero crossing here, if you know at what frequencies the zero crossing happens, you know what magnetic field you have, because you have a magnetometer whose standard is a gyromagnetic ratio of essentially vacuum electrons, if they're sufficiently weakly spin orbital coupled, and that is basically an electronic device that measures calibration-free and your absolute magnetic field. So this is how we started really in a primitive way, a PCB that was like 1 inch by 1.5 inch in size. And then we put you can hardly see it, this orange area is a glass slab that we flipped on top of it that has the polymer device on it. And these copper lines that's where our magnetic field was produced. 5 years later, the development of this, or actually 4 years later, now 5 years, last year, it looked like this. So we'd scaled it to about 50 microns. And we've really built it not just like two substrates that are flipped together, but really pixel-sized magnetometers, which have a demonstrated sensitivity of about actually 600 nanotesla per square root of hertz. So you can make the absolute sensitivity. So, and of course, we are continuing to pursue this just technologically. Okay, so with this example, now you could say, okay, fine. There's no physics. There's technology that we can derive from this. But there is still a lot to explore. And now I think I have to do the same stunt that I did earlier. Interesting. Never done that. It has done other stunts, though, in the past. Okay, now it should work. Okay. The thing, though, is all I've talked so far about was just one example. And the complexity of these spin-dependent processes is much, much, much bigger. So you have a whole zoo. Yeah, you can draw one cartoon after another, as people have done with like spin manifolds in these types of materials that can interact and that can form spin selection rules that are actually much more complex than this simple example of Pauli blockade, which I invoked earlier for these spin-dependent transitions. Everything that's green here illustrates spin manifolds that have strong spin-spin interactions. The yellow halos are supposed to illustrate weak interaction. And then you just go through the literature, going back as far as the 1960s to more recent works. And there are many, many more cartoons that you find that people have drawn, and you can come up with your own cartoons, and likely there's some probability that you find this. And you see now the challenge when you deal with real materials. Obviously, it's not about cartoons, but in the reality, it's about knowing what happens when and under which environmental conditions when you actually have a material where you suspect some sort of spin-dependent process to occur. How are we going to do this? There's lots and lots of evidence that my story that I presented earlier is true. I told you it took like decades to figure that out. What's the systematics? How do we explore this, and how can we be sure, especially if you have complex situations where some of these mechanisms occur at the same time? And now the approach that you can, and the one approach that you can take, no. Okay. And let's see. Okay, for the third time, okay. Okay, at least I know what to do. I just have to, I hope I don't have to do it with every slide. Very good. So let's take the naive approach. If we suspect that spin manifolds control electronic transition rates, that's my spin manifold, then we just observe the electronic transition rate, and let's say for the examples that I gave you earlier, an electric current, and measure this. And what we started, actually, we did exactly this as a function of time. And then we start to manipulate our spin manifold, and hopefully in the most controlled and most accurate way. And that actually means, in our case, we do this with coherent excitation. So we used pulsed electron paramagnetic resonant excitations, but not as a spectroscopy per se, really just as a coherent manipulation tool. And then we look what our observables that we believe are governed by these processes do. And if the spin controls our observable, then of course there will be some change. If there's a change of current, you can record this. But then the current is, of course, influenced by a whole bunch of materials parameters, dielectric relaxation time, meaning the built-in time constants of these materials, and the whole dynamics of how these spin manifolds govern electronic transitions, etc. And if you looked at the cartoons earlier, this can be complex because there are a lot of electronic transitions involved. So what we do then is, well, we observe this. And what you can do is just say, well, whatever the dynamics is, if we record this and then integrate the current change from the steady state, in other words, we count the charge, then this number of charges that we detect there indicates the change of the number of electronic transitions that took place due to that spin manipulation. And if now these states really govern these transitions through coherent manipulation, then there's some projection of the coherent states that we prepare by means of our pulse parameters, pulse length, intensity, frequency, etc., and project this by means of some observable, by some whatever that mechanism is. And how does this even look like? We know it works because I showed you the data earlier, except these were just magnetoresistance measurements. So now we look at it on a time scale, and really a long time scale, microseconds, meaning we look here on time scales that correspond to the built-in time constants of semiconductor thin film samples. And so there's a plot of the current change for these thin film devices, similar to what I showed you earlier, actually pretty much the same in size and area. The change in current as a function of time and applied magnetic field if you produce a one pulse excitation that's X band, that is around 10 gigahertz at the time t0. And that means an instantaneous one, meaning one whose length is short to that time scale. And what you see is a response at a particular magnetic field, and then you record this, you count your charge carriers, and now my claim is, well, I do a coherent spin measurement. How do I know that? And the answer is, you take this experiment and you repeat it many, many times with changing excitation parameters of your paramagnetic state. And that should give you, for instance, the length of that pulse, and that should give you essentially a projection of this coherent spin dynamics during your application of pulse application. So what you see here is now a plot of this charge that comes out of the integration of that transients that I showed you as a function of pulse length. And here you see again, and also a function of magnetic field, you see again a response around a particular resonant magnetic field. You don't see a response outside of this. If you look at the color scale, that corresponds to 0 charges. But then you see on resonance some sort of dynamics. And that is now the reflection of the coherent spin dynamics of these paramagnetic systems that you excite there, whatever they are. But coming back to this example, if that is so, then the harmonic components of these oscillations, you know, what may that be, a coherently driven oscillation? That's actually a spin-Rabi oscillation. That contains information about, that's a quantum mechanical propagation, so it contains information about the Hamiltonian of your spin system. And how can we extract this? Well, we look at the harmonic components. That means we look at the Fourier transform. So here you have a plot of frequencies, frequency components that you have here, in units of gamma times B1. That is, B1 is the amplitude of your driving strength, field strength. And that means 1 corresponds to a spin 1/2. And you see here, you see a pronounced imprint here. You have these weird shapes. And then you have a straight line here. And then you have something at a spin of 2. And you may say now, well, if gamma times B1, if that frequency, if gamma times B1 corresponds to 1, then and that corresponds to a spin 1/2, then is that at 2 maybe a spin 1? It's not the case. The Rabi frequency of a spin 1 is gamma times B1 times square root of 2, which we don't see here. So this is essentially a spin beat oscillation. So it's a beat oscillation between 2 spin 1/2 systems. What we also see, the other features, so this one here, this is a hyperbolic function that's well described by Rabi's frequency formula. So we learned something about the distribution of local hyperfine fields that these paramagnetic states that produce this reflect equally to the vertical line. And so there's lots and lots of information that we can out of this. We can now model our Hamiltonian, and this particular effect that you see here is indeed, and it's the Pauli spin blockade that I talked about earlier. What you see here, kind of the revealing feature, is this factor of 2 spin beat oscillation. That is simply what you do there is you turn one of the charge carriers, let's say an electron, while your hole sits in a place, and that oscillates at gamma times B1, and that controls your current due to the Pauli exclusion principle. If you do the same with the hole while the electron sits and is not excited, you get the same similar signal. That corresponds to these two features. If you turn both at the same time, then your electronic transition rate is governed by the beat oscillation of these two spin nutations. And beat oscillation is the sum and the difference of the individual frequencies. That's exactly what you see here. And in fact, something that you see when you get frequency components close to 0. So we can literally do spectroscopy with the spin Hamiltonia. And then we can, once we have this data, this evidence, then we can open our book again, look at cartoons and say, well, the strength of this approach is not you confirm some model, some cartoon, but the strength is really in that you actually refute most of the cartoons that you find and can exclude these. And that's, of course, that's what science ultimately wants to accomplish. And it's not confirming models, but refuting models. To show you other examples, we're still talking about room temperature MEH PPV, and the usual procedure, I'm used to this now, is like P.PSS. P.PSS, it's a, polystyrene sulfonate doped polyethylene dioxide thiophene, still polymers, but it's a polymer blend, widely used in anti-reflection coatings, not anti-reflection, anti-static coatings. You find it from car windshields to all sorts of, again, cell phone displays, etc., etc. You see here, and this is low temperature data though, at low temperatures when you decrease the mobility sufficiently such that electronic transitions become sufficiently slow. You see here the imprint of all sorts of Rabi oscillation components. Here's again the Fourier transform, and now you see these Rabi hyperbolas very, very pronounced, which again, it's remarkable that a polymer thin film device shows this behavior in its current. In principle, you can do it with organic electronics, these kind of experiments that you carry around in your pocket. And again, you learn something about it. What do we learn here from this example? So compare our measurement with the simulation of spin-dependent rates that we prepared really for a super simplified case of two pairs, two spin-1/2 pairs that have absolutely no coupling whatsoever. Coupling is 0. And you see there's a great similarity, but of course not identity between the simulation and the experimental data. So it's fair to conclude from just this crude comparison that, that these are weakly spin-spin coupled pairs that we see here. But if you compare now the Rabi frequencies for these different magnetic field conditions and the applied frequency that is calculated from those that are measured, so that brings us to the plot that is given here. And you look at again, the beat component, then you see, again, great overlap between data and the calculations, except you need to look closer. There's a slight deviation here on resonance, where it's not exactly the same. And of course, how can we plot this nicely? We take our data and subtract our calculations and plot the difference. And then we get this plot here. And you see now, of course, of resonance, our signal disappears. That means our errors get really big. But on resonance, we see that even with the given uncertainties, there's a clear difference between the calculated uncoupled pairs and the actual pairs that we find in this material. And that shows now the sensitivity of this kind of current detected spectroscopy. We see a deviation somewhere in the hundreds of kilohertz range, definitely below megahertz. And we know this reflects now the spin-spin interactions. That could be exchanged, that can be dipolar. And now if you dig deeper and take these values that you measure here apart, by using the spectral dependence actually of this deviation, then you can narrow it down to values of J and, well, a range for J. So J has to be smaller than 30 nanoelectron volt. And J and D has to be around 23, 24 nanoelectron volts. Meaning, if you know the dipolar coupling now you know how big these pairs are, because magnetic dipolar interaction, of course, goes with 1 over r to the 3. And that means you can essentially determine the expectation value for these pairs that produce here. And that kind of shows the sensitivity and the insights that you get with this spectroscopy. Another example, and that goes back to the collaboration with Brian that we had. So that's where collaboration with someone who understands nuclear spin spectroscopy becomes relevant. Once you see Rabi oscillation, meaning coherent spin motion, in your electric current, you can open an EPR textbook and apply now all the EPR pulse sequences that are known from traditional inductively detected EPR spectroscopy. You have to modify them a little bit, don't want to go into the details. But then if you do that, you can measure all sorts of observables. Now you can measure T1, T2. So you can, for instance, carry out a charge or current detected electron spin echo that you show here. Again, you need an extra pulse. Don't want to go into details. And then you see a spin echo in the electric current. Once you see a spin echo, then you can measure the echo decay. For instance, and these are two different measurements. This was actually done before we did this. We did this when we really have learned how to do it noise-free. So these echoes are noisier. But you can still determine a decay as a function of your pi half to pi pulse delay time, and therefore see the coherent decay of your coherent spin ensemble. And from this, you can derive your T2 times, the true quantum coherence times of your charge carrier spins. From this, then, you can also measure T1 times. And from all this, you can then, combining it with mobilities that you find in these systems, for instance, spin diffusion lengths. And that brings us back to what I mentioned earlier. Yes, you gain in coherence times and spin relaxation times. Both T1 and T2 are longer in these systems generally. Remarkably, because of hyperfine fields, they're all basically within the same order of magnitude, but you lose with mobilities. And again, that's a different topic to bring this together. But at least we have the experiment to scrutinize these observables, which is what we need to in order to optimize spin diffusion in these materials. Now, another experiment that you can do, and again, that brings me back, as I mentioned, to the collaboration with Brian. Once you can measure echoes, you measure echo decay. And now you may say, well, on the previous slides, that seemed to be like a really smooth function. Where do all these wiggles come from? Is this noise? Was this a bad experiment? Or actually, this was an experiment where we had learned how to do these echoes very quickly. So we could actually measure lots and lots and lots of time, lots of data, and all of a sudden we realize we have all these weird wiggles here. And that it's not noise is what you realize immediately when you Fourier transform the wiggles. And what you get here is this frequency component. So this is magnetic field scale. Again, that's around the electron spin resonance frequency where this occurs. And you get something like 14.5 megahertz, which for the applied magnetic field here around 342 to 346 millitesla corresponds to the proton Larmor frequency. And so what this is actually, these wiggles is a modulation of your electron spin echo decay by nuclear spin motion of your protons. That's a pretty daring claim. Just because the numbers fit here, that's not a proof, of course. So we did what I already introduced earlier. Yeah, you can zoom in here, so it's around 14.5. However, note, it's hard to see here. You see already this frequency around 14.5 seems, it's not significant because of the width and the fuzziness of these features. Shifted a little bit to lower frequencies and lower magnetic fields. So that's kind of consistent, but no proof, of course. So what you do is you repeat the same experiment with the same polymer, but you replace your, again, hydrogen by deuterium, and then you repeat it, and all of a sudden your oscillation has a low frequency, and all of a sudden this signal is mostly shifted here to a frequency that's 6 times smaller, not completely, because some hydrogen were actually left here. This was not completely deuterated. And that basically tells you that this imprint here tells you that, yes, that's actually nuclear spins. Think about what the Zeeman energies are at like 300 millitesla and room temperature. This is room temperature again. What the nuclear spin polarization is, it's 0. It's calculated, takes the Boltzmann factor, it's 0. Nuclear spin states control the electric currents in devices where we have applied somewhere a voltage between 1 and 2 volts, or actually 1 and 2.5 volts. I don't know exactly what this is here. We're talking about electron volts, orders of magnitudes bigger than the thermal energies, but the thermal energies are basically 6 orders of magnitude bigger than the states with which we do spectroscopy here. That is interesting. Now, yeah, once you can do this, you know you can do electrically detected NMR. And just one data set, that's the electrically detected NMR spectra of protons in these organic semiconductors. Why is this so wide here? Well, that's the distribution essentially. Why do we have a resonance that peaks at about 13 megahertz? Well, that's approximately, that corresponds to our applied magnetic field. But why is it so wide? Basically, on the width of that resonance is on the order of the frequency where it resonates. That is because this distribution reflects all the individual hyperfine interactions that hydrogen has with nearby charge carrier states, these polaronic states of electrons and holes in this material. Now finally, coming back to SOC, spin-orbit coupling. All of this, all of what I've talked about so far happened under the assumption that, that there's weak spin-orbit coupling, and that works fairly well. You always assume it's zero. You know, we know how important spin-orbit is for any sort of spintronic scheme that we may think about. It may be weak, but of course it's not zero in these materials either. So, how can we access this? We know in comparison to these quantities that remarkably we can measure here, which are already very small, it may be hard to detect it. And how do you detect the influence of spin-orbit coupling, especially since this is such a complicated observable anyway, because it really is different for every electronic state, and there's a whole continuum in these materials, of course, like in any condensed matter system. So that's a really difficult question. And where spin-orbit coupling really influences magnetic resonance, or let's say electron paramagnetic resonances, is, of course, by means of the Landé G-factor, the effective Landé factor, the deviation of the Landé factor that we detect here, relative to the vacuum Landé factor of 2.0023 something that comes out of QED, basically. So now we're in the business of measuring G-factors, basically. The problem is, if you have any sort of disorder or complexity in your material, that will be distributed. That's actually called G-strain, the random distribution of G-factor deviations. And on top of this, we know already, in a sense, I've not really shown it, but it's kind of clear. I've shown that our magnetic resonance lines that we see here are governed by hyperfine fields. So whatever the effect is, it's buried under everything that I've talked about so far. That's just too bad. The thing is, though, if these effects express themselves in G-strain, that also means I just have to basically cover a large magnetic field range under which I just repeat the experiments that I've talked about here earlier. So far, most of what I've done here, these electrically detected magnetic resonant manipulations, all of this was done at around at an excitation frequency around 10 gigahertz, around magnetic fields of somewhere about 350 millitesla. That's what all of this has been. Now we repeat this in a magnetic field range of, okay, let me show that. It's actually good. Turn it off and then throw it up there, if it does it. Yes, somewhere between 1 millitesla. And yes, we can detect magnetic resonance at 1 millitesla. I've explained earlier that you can, all the way to about 10 Tesla. Actually, 12 Tesla was our highest magnetic fields that we've applied. That corresponds to a frequency range of roughly 100 megahertz to 336 gigahertz. And so we're not quite at the sometime soon we'll do it at 700 gigahertz, so maybe we will get to terahertz. And if you do this, if you look at this plot, you finally understand why resonance lines are called resonance lines, because we have all these lines here. And now, of course, you want to expand them and do line shape analysis under all these conditions. Which looks for this material, now I'm back at P.PSS, which looks like this. And you see actually at 100 megahertz, and then you jump here. This is only a subset, of course, of the data I showed on the previous slide. We jump here to 3 gigahertz and 9 gigahertz. There's little change. You see they're getting broader, but not much. I increase here my width by my frequency roughly by a factor 100, and my width maybe increases by a factor 2, maybe. But then you go from 10 gigahertz to 336 gigahertz, factor 30, and your width increases by a factor 30, roughly. And that tells you that with this data is governed by the line shape by spin-orbit coupling, whereas this data here is governed by hyperfine fields. So you have a way to completely separate spin-orbit influences from hyperfine influences. And now you can study this. You have a handle on it. You do it with P.PSS. You do it with polyfluorine. You do it with MEH PPV, what I talked about earlier. you do it. What else did we do it? Oh, proprietary polymers. We use commercial polymers that actually companies developed and built devices out of it. And if you do all this, then you see that you get in this domain, this high magnetic field domain, 12 Tesla, where spin-orbit coupling governs these lines, you see all of a sudden line shapes that you cannot straightforwardly explain with this two charge carrier G-strain model, which is essentially, it goes back to fits with two Gaussian functions due to the randomness of this. We've done this here, and you see with P.PSS it works wonderfully. But you see, like with these other polymers, and these are room temperature measurements for these three polymers here, it totally does, you can't fit that anymore, even though these are actually functions with great versatility. Usually if you have 4 fit parameters, you can fit an elephant. You can't do that here. So that's proof that the model simply doesn't work. And it's proof that there's more complexity in these lines. And that's actually the richness of that data. What can you now learn from that data? So what you can do now is to say, okay, we know it's complicated. And now we go back and we take these chemical structures, these polymers, this is example of MEH-PPV. We use density functional theory to actually calculate wave functions of these electronic states. And once we do this, we can scrutinize whether these wave functions actually give us the right predictions for what we think is happening here. So we take the G-strain, basically the spin-orbit mediated effects on our resonances, and make predictions. We take calculations, not fit our data, we calculate our data based on these predictions. And yeah, we take also hyperfine fields that we measure at low magnetic fields and plug them in there. So we combine it with experimental data that is corroborated, and then we just compare. And what comes out of this is, well, experimental data compared to calculations, and then for different cases where we looked at ordered polymers in one way, and then polymers that were ordered where the side groups were ordered in a different way, so in a completely anti-symmetric way and then a completely symmetric way. In reality, it's neither one of these two, but it has to be somewhere in between. And then we also looked at which of these states that we calculated, the HOMO state and the LUMO state, corresponds to the two resonances that we assume here. So you get 4 different combinations reflected by red and blue and dashed and non-dashed respectively. And if you compare now this calculated data with the experimental data, you see like these red cases, they just don't fit. There's no agreement. So that also shows that we can't just reproduce anything. But then you see the blue works really well. And that actually excludes the assumption of G-strain, which basically in a way we are more selective for the description that we make here. And that essentially tells us that this data contains really unambiguous information about the nature of these wave functions. The wave functions are calculated, but here we have an experimental way to scrutinize those. And that's what we've done. So essentially, you can say, yeah, you measure your wave function, which of course what you don't do, but you measure data that can be scrutinized by DFT, where your DFT predictions can be tested ultimately. So with this all being said, I basically want to summarize what I talked about. We use spin-dependent transitions for the examples that I talked about today in organic semiconductors in order to learn, first and most of all, something about the qualitative nature. That means to decide, well, which cartoons are actually wrong that people have drawn about these materials. And that really narrows it down. But then, once we understand the qualitative nature, we can really learn something about the dynamics of these transitions and the dynamics of these spin manifolds that are involved there. We can learn something about the quantitative nature of the spin coupling in these systems. I showed hyperfine coupling effects, meaning nuclear spin effects. I showed how to measure spin exchange by analyzing essentially your Rabi wiggles, your Rabi frequency shifts, and spin dipolar interaction. That tells you something about distances. And then if you look at spin-orbit interactions, then it gets complicated. But in combination with simulation, with theoretical data, you can also obtain some fairly unambiguous insights into the nature of your systems. And in the end, that also reveals your G tensors, your G strain, and then even wave functions that you can scrutinize. And that hopefully brings clarity into this mess of cartoons that the past 40 years have essentially produced there. And with this, briefly, one last statement about the work that we're doing right now, and that is, and maybe that's a sign that I should really wrap it up now. That is what we're doing right now is when we talk about spintronics. Now we have spin-dependent processes, basically a material. We have materials in which spin manifolds, except these are permutation symmetry states, can be measured electrically. That's what you need for spintronics. So we essentially have spin manifolds that are information carriers. But if we want to manipulate, but if we want to use this as information carriers, we want to be able to manipulate them. And that's exactly, what we need. For spintronics, you need spin measurement. I've just shown in the past hour how to do this, how to measure with electric current spins. I've also shown implicitly how to initialize these systems, namely by applying a bias and having an electric current, because you pump triplet states, so you pump permutation symmetry and oppress permutation anti-symmetry. But I've not said anything about spin manipulation. And that's exactly what we are working on right now. So we are building, we want to manipulate spins, obviously not by spin-orbit coupling, because that's very weak. So Rashba interaction or Dresselhaus, based spin manipulation is not really feasible. But maybe electric field manipulation, because in these floppy materials, we can manipulate distances through electric fields. And does this work? I mean, do we have first data that kind of supports this hypothesis? I mean, that's another cartoon. And that tells us that electrons are blue and holes are red, and not much more. What gives us hope that we're not completely off is if you apply electric fields to these systems and then you look at these spin-controlled currents, you get really strong changes of these signals. So your rate on resonance, so essentially your current change due to magnetic resonance is quenched basically by 50%, by half. And that's consistent with randomly oriented pairs where half of them you pull apart due to the random orientation, whereas the other half you pull closer together, and therefore you cut out half of your electronic transition rate. If this is true and corroborated, that's only a proof that electric field influences your signal, not that it manipulates spin. Then you can think about adiabatically changing the distance between your spins and controlling with electric fields adiabatically interaction Hamiltonians, such as dipolar interaction, and then using this for a gate-controlled, an electric field-controlled spin manipulation of these permutation symmetry states in these materials. And with this outlook, I want to thank all the collaborators shame on me. Where's Brian here? I had him. That is actually, Brian contributed to the nuclear work, and I know exactly why he flew out here recently, because shame on me. I did not check this. So Brian is in this list, and basically my main, Paul Byrne actually provided the isotopically pure material. Stefan Grimme recently did the DFT calculations. This is Hans van Tol from the MAG lab. This is where we did the 12 Tesla measurements. So we cover in my lab everything from, well, by now 10 megahertz to 20 gigahertz roughly. But above this, we are not able to sweep quickly up to all the way to 12 Tesla. And then there's Wally and Misha when it comes to materials and then really analytical calculations. And then, of course, there's John Lupton. He just is always there. Those people who know him know that he's into organic materials for a long time. Everyone else are group members who have contributed. And I don't know why that happened. I hope that's not a Freudian. I have to show Brian after this talk my past 20 talks that I've given at the ENC to prove he's actually on there. This is just terrible. Okay, with this being said, I leave it here. My computer just gave up in the right moment, 60 minutes. Thanks.
Spectacular stuff. Do we have questions for Christoph?
There's one.
Do you have any more apparatus? I mean, you had a nice diagram near the end, but I'd just like to see some more apparatus about
Pictures of how we do this.
Pictures of how you do
Yeah,
it.
right. So I don't have not in this one, an overview about all of our machines, but you saw at the latest when I showed you this plot about our not quite 5 orders, but more than 4 orders of magnitudes in magnetic field and frequencies that we cover there, that you actually do not just have one setup. Because when everyone who's familiar with, let's say, commercial EPR spectroscopy knows you spend about $1 million and then you get some big machine, and that has exactly not one frequency, but let's say a range of 9.3 gigahertz to 9.7 gigahertz or so. That would be X-band. And then you spend another $1 million if you want 20 gigahertz or something. The reason why this is so is because you need to build everything for particular wavelengths, mostly for detection. And we don't detect EPR inductively. So all we have to accomplish is excitation. And that makes it easier. So let me see, because there are so many interesting pictures but this thing basically has collapsed now anyway. So what we do is to basically cover basically the range from a megahertz to a gigahertz is RF coils. That's the same approach as NMR spectroscopy, because they developed all that. So we have lots and lots of coils, and making these is not a big deal. So that's easy. It gets non-trivial starting at a gigahertz all the way to, well, it's never trivial beyond that, but let's say 1 gigahertz to 20 gigahertz. We cover this mostly with so we have the advantage that all of our devices are thin film devices. So you don't need to excite a large volume. So what we do is we designed coplanar waveguides. So it's basically thin film resonators. And the beauty of we have capacitively coupled coplanar waveguides, all basically in the form of PCBs with special substrates that have low dielectric losses. So you cannot take standard PCBs, but these are PCBs essentially. And if you design them right, then they have a fundamental frequency. It's lambda over 4. But the beauty is you can excite higher harmonics. And that gives you not a continuous spectrum, but it gives you multiple integers. So now you can cover higher harmonics and essentially fill out the whole frequency range. Let me see if I have this somewhere here. That would be just because it's, hang on, this one. Okay, I take randomly and I have no idea if it's in here. Yeah, very good. So that's this coplanar waveguide setup. Yeah, so here's essentially that is, that's a lambda over 4, and we put our samples on top. You see a simulation here. You only get good excitation fields, and we really did this for an OLED with a contact layer, which also messes with our magnetic field. That's a simulation. You need to be, let's say, within a few tenths of micrometers in order to have reasonable fields. But then you get reasonable excitation fields. And again, that's lambda over 4, and you can take higher harmonics. And if you look at, this is data for MEH PPBs that I didn't show earlier. The different colors here represent to different resonators, different lambda over 4, and their higher harmonics. And by doing this, we can cover a whole range of frequencies. And then, of course, for high magnetic fields and frequencies, essentially past 20 gigahertz, then you have to do it optically. So then you have a quasi-optical setup, basically a terahertz setup, and you use corrugated waveguides to couple your millimeter waves then into your samples, and that's a whole different, then you need a millimeter wave optics. And so, and again, we use for this a lot of the technology in Tallahassee, and that, however, still doesn't mean that we can just go to Tallahassee and turn it on, because we are doing what they never do, and that is EDMR. And so we had to essentially build our own EDMR setup. So this is this Jan van Tol at the Mag Lab. This is not the setup. This is just the detection setup. The actual magnet is below this. It's a gigantic magnet in the floor under this. And what we built for this is essentially a sample holder and contact setup that does not mess with these millimeter waves. That's the flange, the end flange of the corrugated waveguide, and then we have a particular EDMR sample scheme. So it's lots and lots of technologies, and now I spent 5 minutes answering a question. I don't know if that helped.
Any other questions for Christoph? If not, I think we should thank our speaker again.
Thanks.